Lesson 6.7, exponential functions. Our objective for this lesson is to be able to model an exponential function using an equation, a table, and a graph. An exponential function grows or decays by the same relative amount per unit time. So remember, we defined a function as a relationship between two quantities where one quantity depends on the other. And an exponential function is one that exhibits exponential growth or decay. And that exponential growth or decay is where it's growing or decaying by the same relative amount, as opposed to the same absolute amount that we saw with linear growth or decay. All right, so here is the general formula for an exponential function. It's going to have the form q equals q naught times 1 plus r to the t power, where q is the value of the exponentially growing or decaying quantity at time t. Q naught, that's that q with the little subscript 0. Whenever we have that subscript 0, we usually use that to refer to an initial quantity, an initial value. So Q naught here is equal to the initial value of the quantity. That is the quantity at time 0. R is the growth rate for the quantity, or the decay rate if R is less than 0. And T is going to be the time. So you should recognize this function as being very similar to the interest functions that we learned about when we were talking about money, where we had A, the amount in our account, is equal to the principal times 1 plus R to the t power, where R was the interest rate. Well, here that is the same sort of principle, where we're talking about a growth rate, and again, that growth rate has to be as a decimal as opposed to a percentage. So our general function is going to be q equals q naught times the quantity 1 plus r taken to the t power. Our example says the 2010 census found a U.S. population of about 309 million with an estimated growth rate of 0.9% per year. Write an equation for the U.S. population that assumes exponential growth at this rate. Create a table showing the U.S. population every 10 years until 2060, then make a graph of the exponential function. All right, so let's start by defining our variables. So with all of these functions, we're going to see exponential growth over time. So time is going to be our independent variable. So let's write that first. T is going to be time, and it's going to be time in years because we know the growth rate per year. And we want this to be time since 2010. Since we know the population in 2010, we want our initial value to be that population in 2010. So our initial year is going to be 2010. That's going to be when t equals 0. All right, so now we need another variable. Let's call it p. This is going to be our dependent variable, and that's going to be the U.S. population. And let's go ahead and make this easier on ourselves, and we're going to say that this is in millions. So we don't have to continue to write out that this is 309 million. We can just put 309 in our function. All right, so now our general formula we said was q equals q naught times 1 plus r to the t power. So our population, our dependent variable is p, and it's going to be equal to our initial value, which was 309 million, but we're just going to write 309 since we defined our dependent variable to be in millions. And we're going to multiply that now by 1 plus our growth rate. Now, we need to be careful here because a lot of people see a growth rate like this, 0.9%, and think, oh, that's already in decimal form. But be careful, it's still a percentage. We still need to divide this by 100. So instead of 0.9, this is going to be 0.009. So 0.009, and we'll go ahead and just add it on to that 1 there. And then take that to the t power. So we still have our dependent and our independent variable in our function, and we filled in our initial value and our growth rate. All right, so there's our equation. Now let's take this equation and make a table of values. So we'll have our independent variable on the left and our dependent variable on the right. And we want every 10 years until 2060. So that'll be up to t equals 50. So we'll go from 0, then 10, 20, 30, 40, and 50. Our p at time 0 is going to be 309. We know that. We were given that as our initial value. And then if we plug in 10, 20, 30, 40, and 50 in for t, at 10 we're going to get 338.0. We'll round this to the nearest tenth. At 20 we get 369.6. 30 we get 404.3. At 40 we're going to get 442.2. And at 50, we're going to get 483.6. And of course, I already entered those into a calculator earlier. All right, so now once we have this table of values, let's create a graph. So we're going to have our independent variable on the horizontal axis here. And let's go 10, 20, 30, 40, 50 years out. And then on the vertical axis, we're going to have our population. So let's go 100, 200, 300, 400, and 500. And in year 0, we had a population of 309. Nope, that's 200. I need to go up one more, 309. At year 10, we had 338. That's going to be just a little bit higher there. And then at 20, we're at 369. So about there. At 30, we're at 400, just over 400. At year 40, we're at 442. Let's put that about right there. And then at 50, we're at 483. All right. So we can start to see a little bit of a curve upward here. Now we haven't yet seen that characteristic L shape that we expect to see with exponential growth, and that's because this is a small growth rate, and it's only over 50 years. If we were to continue this out another 100 years, we'd start to see that L shape for an exponential curve.